Okay, so today we're going to do our fourth lesson out of the 5 in stoichiometry unit. We're going to talk about limiting reactant calculations. So no new, there's a little bit of newness. You're going to compare one reaction to another. But as far as like ideas, it's pretty much something you've already known. So we're going to calculate limiting reactant using two mass-to-mass calculations. So what is that transition? So basically, the limiting reactant is the one that will run out first, and it limits the amount of product that can be made, okay? So we're actually going to calculate two mass-to-mass calculations, okay? And then you're going to pick the limiting reactant, which is just the one that will yield the smaller amount. So a real world example is basically, I don't know if you guys even know what this is, but we're going to look at like a recipe, okay? So basically, if you are making, I guess, cupcakes or something, and you have, okay, so in America we have a bag of mix, okay? We don't like make stuff from scratch. So we have one mix, okay, and we use 3 eggs. And we're just going to say 2 oils, okay? And a pan, we'll make a pan of cupcakes. So if you don't have this much of each of these, you can't make a full pan. So what we're looking for is a limiting reactant. So if we only have like, let's say you have 3 mixes, okay? So if you make 3 mixes, okay, how many pans can you make? So basically, if you have 3 mixes, you can make 3 pans, okay? Let's say you have 15 eggs, okay? So you have 15 eggs. How many pans can you make? So what you're doing is you're just kind of, this would be considered the mole-to-mole ratio, okay? So basically, a real-world example of stoichiometry is what you do in your recipes every day. So like if your mom's having company and she's making, I don't know, moussaka, and you need like triple the amount because you have a bunch of family coming. Don't make fun of me for that. But if you have a bunch of family coming, you just, to make triple the amount of the moussaka, then you would have to triple the amount of ingredients. And that's pretty much what stoichiometry is. So it's actually super simple. We're going to go back to chemistry. It's just a real world example. You don't have to write a lot of notes on that. You won't see that on the test, but it's kind of, I get this question a lot. Miss, what does this have to do with real life? You basically do it in real life with your recipes. Chemists do it in real life with reactions. So that's it. All right. These equations are pretty involved, okay? And it's nothing new. You just have to do something twice, okay? So you have to do what we've been doing twice, and you're just comparing and picking the smallest product, okay? So our first example will be if 17.1 grams of potassium reacts with this many grams of fluorine, which reactant is the limiting reactant and what mass of potassium fluoride can theoretically be produced? So it's giving us 2 reactants and the masses. So we don't know which one. So it's like giving us like, I don't know, eggs and mix, okay? So one of these, if we have a certain amount of each one, one's going to limit how many pans. If we're making a sandwich and it takes 2 pieces of bread for every 1 piece of cheese, okay, or meat, whatever, if you have 100 pieces of bread, and only 1 piece of meat, you can still only make 1 sandwich, okay? So one of those is a limiting reactant, and we're just going to find out which one. So first we need to do the word equation, okay? So potassium and fluorine are reacting. It's going to be a synthesis reaction. You just bring them down. Potassium's not a diatomic element, but fluorine is diatomic, so you would bring down F2. And potassium fluoride, they're a 1-to-1 ratio. Then you need to balance, so 2 potassiums here, 2 potassiums here, 2 fluorines, 2 fluorines. All right, so we have been given 17.1 grams of potassium in the question, and we were given 14.3 grams of fluorine in the question as well. We need to find out how much of this can theoretically be produced. Right. So we have two equations that we're going to do. We're going to first do the equation for this one, okay, so for potassium and how many grams of this. So the known will be this and unknown will be this for the first equation. For the second equation, we do this as the known and this is the unknown, okay? So we're doing the same thing we've been doing, it's just we're doing it twice and then we're going to compare. All right, so our known is 17.1 grams of potassium. We write it down because it's our known. We need to convert to moles, okay? So we just grab this mass off the periodic table. That's how much it weighs per mole. So that's just a conversion. It's not a mole to mole ratio. Then we need to do our mole to mole ratio. So for every 2 moles of potassium, okay, potassium fluoride, sorry, you have 2 moles of potassium, okay? So that's the 2 to 2 ratio. So now we're at moles of potassium fluoride, but we want grams of potassium fluoride. So we need to convert that, and this is a conversion unit, okay? So we just grab these numbers off the periodic table, add them together, and we have our conversion right here, okay? So the moles will cancel out, and we will have this mass, okay? So now we just plug it into the calculator. This 17.1 divided by 39.1 times 2 divided by 2 times 58.1, and that's our answer. So we have halfway done. So we're going to do the second one. So now we just use this as the known, this as the unknown, and then we'll compare, okay? So we always write our known first, which is here, okay? We need to convert to moles. We're basically doing the same thing, right? Unless I'm mean and I give you not a mass here, I don't know. So you have 14.3 grams of fluorine. And then we grab the mass, the molar mass off the periodic table. Don't forget to multiply it by 2 because there's 2 atoms of it. That's how much 1 mole of it will weigh, okay? Now we need to do our mole to mole ratio because we don't really want fluorine as our answer. We want potassium fluoride, okay? So the moles of fluorine will go away and we are left with moles of potassium fluoride. We don't want moles of potassium fluoride. We're good with the element or the compound, but we need grams and not moles. So we need to convert moles to grams, which is what's happening in this step. And this number we just got from the periodic table. We added the mass of potassium plus the mass of fluorine, and that's what we got. Okay, so in our calculator, we take this number divided by this number times this number times this number, and we have, this is our answer. So this is what we've been doing basically the whole unit. Same thing with this one. It's just we did it twice. We were given 2 different masses of something. We need to find out how much of the product it'll make in each case. And this is how much. So if we have this much potassium, this is the maximum amount of potassium fluoride we can make. If we have this much fluorine, this is the maximum amount of potassium fluoride we can make. So that means the lowest one, so with the limiting reactant, that means, potassium is the limiting reactant, the one that has the lowest amount, okay? So even if we had 100 grams of fluorine, we still can't make any more than this if this is all the potassium that we have, okay? So limiting reactant is just, you know, what's the most product we can make with that amount. It doesn't matter if we have 1,000 pieces of bread. If we have 2 pieces of meat, we can only make 2 sandwiches, okay? So that's basically the idea behind limiting reactant. All right, let's do number 5 on the homework problems. If 5.3 grams of gallium reacts with 5.3 grams of oxygen, so gallium is reacting with oxygen, how many grams of gallium oxide will be produced? Gallium oxide. Okay, so there's our word equation. Formula equation, gallium is not a diatomic element, but oxygen is. Gallium oxide. Gallium is a +3 charge. Oxygen is a -2. Bring down those charges. That's actually one of the questions on y'all's midterm today. Ga2O3. Now we have our formula equation, but we need to balance it. So 1 gallium, 2 galliums, 2 oxygens, 3 oxygens. So we need to write 2 here, 3 here. That makes 4 gallium, so we need to change that to 4. Okay, so 4 galliums, 4, 6 oxygens, 6 oxygens, we're good. All right, so limiting reactant. So basically we have 2 equations we're doing now, okay? So we need to find out, we have 5.3 grams of gallium, 5.3 grams of gallium. We have 5.3 grams of oxygen. You would think that if you have the same amount of each, there would be no limiting reactant, but let's just find out. Okay, so our known, we're gonna have 2 knowns, okay, and 2 unknowns. So 1 known, 1 unknown, 1 known, 1 unknown. Okay, so our first known will be 5.3 grams of gallium, okay, and the unknown will be the same for both, okay. We're both trying to find out how many grams of gallium oxide, grams of gallium oxide. Okay, and then the other known here is 5.3 grams of oxygen. Okay, so we always start with our known, okay? We're gonna basically do both of our equations and find out which one's the least, and that's our limiting reactant, and we're done. So we take our known, which is 5.3 grams of gallium, okay? We need to convert that to moles so we can do a mole to mole ratio. So we need to find out how much gallium weighs, which is 69.723. Okay, so we have that done. So grams of gallium are gone. We have moles of gallium, which go here. Now we do our mole to mole ratio. So we have 4 moles of gallium for every 2 moles of gallium oxide. Oops, moles. Okay, so we have our mole to mole ratio. That's good. Now we have 1 mole of gallium oxide. And our unknown will be grams of gallium oxide. So how many grams of gallium oxide? So basically, gallium weighs 69.723 times, we had 2 of them, I think, 2, plus oxygen, which is 15.999, times, we had 3 of them. Let me make sure before I mess everything. Yeah, 3 of them, close parentheses, equals. So it weighs 187.44. 187.44. Okay. So we just calculate it now. So we take 5.3 divided by 69.723 times 2 divided by 4 times 187.44. 7.12, we have 2 significant figures, so 7.1 grams of gallium oxide can be produced with that amount. Okay, we need to find out the other amount. Next we do 5.3 grams of oxygen. Okay, we need to convert that to moles of oxygen. Oxygen weighs 16 each, or 15.99 times 2. So we're going to say 32 grams of oxygen. Okay, we need to do a mole to mole ratio. So we do conversion, mole to mole ratio, conversion. Okay, moles of Ga2O3, moles of oxygen. So we have 3 moles of oxygen. sorry. 3 moles of oxygen, 3 moles of oxygen, 2 moles of gallium oxide. And then here we've already calculated it, so 187.44 grams of gallium oxide for every 1 mole of it. Okay, so now we just plug that into the calculator. Sorry. Okay, so 5.3 divided by 32 times 2 divided by 3 times 187.44, and your answer is 20 point, oh, that's it, 20 point grams of gallium oxide. All right, so now we need to find the limiting reactant. So basically, this one is smaller. So the limiting reactant is gallium. Okay, so the limiting reactant is gallium. And that's your answer.